Welcome to a lesson with Dr. Powell. Let's take a look at solving a system of congruences, this time with 3. Let's suppose we have x is congruent with 3 different equations. And let's suppose that our mods are 5, 6, and 7. And this is maybe 2, 1, 3. Now, we chose our mods, notice, such that they don't share any common factors. This actually ensures via the Chinese remainder theorem that that we'll have a unique solution for x in z mod 5 times 6 times 7, which is 210 z. So there'll be a unique solution in here for x, meaning that the solutions that actually solve the system are actually a unique, fill out a unique coset of 210z in z, namely one element in here actually as a set or a chunk of z contains all the solutions to the system. So how do we find that? Well, we keep in mind, remember that the solving map from z mod 5z cross z mod 6z cross z mod 7z to z mod 210z is actually a modular map. It preserves addition and outside multiplication by z. And since this solving map is a module map, all we have to do is find the images of 1, 0, 0, 0, 1, 0, and 0, 0, 1. Give these the names of E1, E2, and E3. So, and maybe even a bar, if you will, technically, but I won't use that here, because this isn't really what you call a free Z module. You have some mods in here, which makes it not free. However, we can still think of where these will travel via the map, and then just simply take a sum of multiples of these, of the images of these, in order to get where we land. That's because the module structure is preserved over, and we can represent, for instance, 2, 1, 3 is what we're trying to plug into the solving function or the solving map to solve the system, which is the same thing as 2e1 plus 1e2 plus 3e3. And the image is simply going to be 2 f of e1 plus 1 times f of e2 plus 3 times f of e3. So we just need to solve the system for these, which are fairly simple to do. And then you multiply and add, and then you'll get the solution here. So I claim that finding the image of FE1, which is simply solving the system when you have a 1, 0, 0, is fairly simple. And same thing for E2 and E3. How so? Let's take a look. So if we want to solve the system to find f of E1, we're just looking at 1, 0, 0. How do we solve this system? Well, we need something that's a multiple of 6 and 7. Okay, because it's 0 mod 6 and 0 mod 7. These are relatively prime. You just multiply them together. 6 times 7 is 42. Okay, so it has to be a multiple of 42, whatever we use to solve this system. You also know that it needs to be that whatever we use to solve to solve the system has to be 1 mod 5, meaning that we need to make sure that this is 1 mod, that we take a multiple of this, that's 1 mod 5. Well, right now this is 2 mod 5. We need to multiply it by something to become 1 mod 5. Well, simply by anything that represents an inverse of 2 mod 5. So 3 would work. Also -2 would work, because that would give, let's see, that would be -4, which would be the same as 1. So -2 would work. So we can take -2 times 42. And this will give a solution to this system, and we can take that as f of v1. If so we have, we multiply that out, and we have what? -84. Okay, now this next one, we do the same, a similar thing. V2, we take 5 times 7, which is 35. And then we multiply it by something, so it's 1 mod 6. Right now, this is -1 mod 6, so just take negative. So we get -35, multiply by 1. We're adding. Okay, here for E3, what we do is we do a similar thing. We want 5, we take 5 times 6 because we want it to be a multiple of 5 and 6. So that's 30. But then this also needs to be equal to 1 mod 7. A multiple of this needs to be congruent to 1 mod 7. So we need to we think, well, this is 2 mod 7. So we need to multiply it by 4 would work, or -3 even. -3, because -3 is an inverse mod 7 of 2. So multiplying these together, you'd get something that's 1 mod 7. So that would be what? -90 and 3. Keep in mind that everything that's in here is actually in mod 210, but you could freely just compute this and then figure out a nice representative mod 210 for it. Thanks for watching.